So, welcome everyone. This is, I think, the only talk at 9:30 for the whole week, so I'm glad everybody's here. I was not expecting anyone. All right, so Lie groupoids. Or I think, was it? So there's a lot of things to explain. There's 4 lectures, which is 4 hours, which is a lot of time, but still, I will have to be a little bit skimpy on the index theory part. So that could be another 4 lectures, right? So I'll focus on the Lie groupoid part and try to be a little. I'll give you a little bit of information on index theory, but if you don't know it already, it's probably not going to make a whole lot of sense. But at least hopefully the Lie groupoid part will be the focus of the lectures. Okay, so I'm not going to assume anyone knows anything. So I'll explain. And if you don't know something I'm saying, just please interrupt. Right? This is, I think, is a standing assumption for all the lectures. So groupoid. So I'll start with the algebraic definition, which is the basis of the thing. So it's a small category. So small just means it's a set, okay, and with inverses. Meaning that every morphism is an isomorphism. So it's a category with no other morphisms than isomorphisms. So the 2 extreme examples, of course, a group is a groupoid. There's only one object, right? So there's an object and lots of arrows. They're all invertible. And then the other extreme, okay, there's one name I've seen being used for this is simplicial groupoid, which means that for every pair of objects, there's exactly one arrow. For every ordered pair of objects, exactly one. Meaning, so any 2 objects are isomorphic in exactly one way. Okay, so I'm pressing too hard on my chalk, so I'm going to run through them. Okay, so this is actually so this is easy to construct. So for any set, we'll have what we'll refer to as the pair groupoid, which is the simplicial. Every simplicial groupoid is basically a pair groupoid. Right? So, well, I didn't. Somebody calls it a simplicial groupoid. Sorry? I wouldn't talk about simplicial groups in this week, but I could. It's quite different. Yeah, it's fine. But somebody called it that, and so. Thank you. Okay. Whatever it would be, this is somebody. You can give it another name if you don't like the name. Okay, so since we have categories, we have equivalents of categories. I hope people know what equivalent categories are. So you have equivalent groupoids, which is just groupoids that are equivalent as categories. Okay, we're just doing algebra, right? So there's no complication here. Algebraically, a groupoid is a fairly simple-minded thing. Because, okay, so what is a category up to equivalence? It's basically equivalence class, isomorphism classes of objects. But there's a little bit more. There's automorphism groups. Okay? And that's exactly the difference between just having an equivalence relation and a groupoid. It's automorphism group. So this is up to equivalence. Every groupoid is a disjoint union of groups, right? Where, so this means one object for each isomorphism class. And plus the automorphism groups. Now, so Rolf is not going to do equivalence of groupoids, so I'm also not going to do equivalence of groupoids. So let's say up to isomorphism of groupoids in this case, where the category now, okay, the morphisms are functors of groupoids. It's slightly, only a little bit more information here. A groupoid is basically a disjoint union of a group. So that's the automorphism group. And then there's a simplicial, well, what I'm not allowed to call a simplicial groupoid, but whatever you want to call the thing that I call a simplicial groupoid. Okay? So let's call it a pair groupoid. Okay, so it's actually a fairly boring object if you look at it this way. Okay, so let's give a simple example before I go to Lie groupoids. So the fundamental group is really a fundamental groupoid initially in the most sort of natural way. So if X is a space, right, then our groupoid could be all homotopy types. Of paths in X. Right, so that's a groupoid, and the object space is, of course, just X. Okay, so in up to equivalence, as I said, it's basically the fundamental groups of the connected components of the space. That's the way you pick it. Okay, so that's the algebraic part. Let's not. Any questions? Fairly straightforward, I hope. Okay. I should count to 10. Sorry? Algebroids? There aren't any algebroids yet, so we need Lie groupoids first. Yeah. That's what I'm going to do next. So from our point of view, like in non-commutative geometry, the groupoids become interesting when these basically so these algebraic gadgets are somehow collected in a total manifold. In the same way that, okay, so a vector bundle algebraically is a disjoint union of vector spaces. Typically uncountably many, and then so they're all basically the same. It's very boring. But a vector space, these vector spaces are embedded in a total space, and that's what makes it a rich object or a useful object. So it's kind of like a connecting tissue that connects algebraically disconnected structures into a smooth family. Okay, so the idea of Lie groupoids or smooth groupoids is similar. Algebraically, typically these groupoids are fairly simple-minded, but what makes them useful is that they're embedded in a smooth manifold, in a smooth structure. Okay, so Lie groupoid, which is, as far as I know, the same as a smooth groupoid. Let me explain what it means for a groupoid to be smooth. So introduce some notation now. Typically, for most people who work with groupoids, they think of the groupoids itself as the set of morphisms or arrows. That's typically the G. Okay, just as in, I said, one object category is a group. The arrows form a group, obviously. Okay, so this is the object. No, sorry, the arrows or morphisms. This is supposed to be a manifold, of course, just as for a Lie group. The set of objects, which is often denoted as G sub 0, is also supposed to be a smooth manifold. And also, a lot of groupoid people actually identify the object space as a subset of the space of arrows by identifying each object basically with the, right, every object has an identity morphism or a unit, right, unit in the automorphism group, and that you just identify that element with the object. So that's it. So if in this case though, for these are smooth groupoids, you want this to be a submanifold. I guess the term is embedded. I can never remember these things. Immersed, embedded. It's embedded, I think, but whatever the correct term is. I don't have good memory. All right, so then various maps have to be smooth maps. So first of all, there are the range and source maps, or also sometimes called target. Right, so every arrow has an object at the source and an object at the as its target or range. These have to be smooth maps. And for later purposes, or well, it'll be clear in a second, there have to be a little bit more. There have to be submersions. But typically, if you work with, you could work with locally compact Hausdorff groupoids, or even locally compact Hausdorff groupoids, or whatever the correct term is. And then these guys have to be open maps, but in this case, you want something even better. You want them to be submersions. And one immediate reason for this is that if you look at the composable arrows, so that's pairs. Okay, and here's a little bit of convention where the source of gamma 1 is the range of gamma 2. So this means that implicitly, let me just draw the picture. The arrows go from right to left. That's just the source, right, that explains this funny, otherwise somewhat puzzling convention. But this turns out to be just useful in many settings. Okay, so because of this here, since these are submersions, this will actually be a manifold. It's one immediate reason for requiring. So this is again automatically a manifold. And you want, of course, the multiplication map or composition to be a smooth map, obviously. So that's another smooth map. And then finally, we have inverses. Right, gamma to gamma inverse. That's a map from G to G, and again, it should be a smooth map. So I think this is a submanifold, smooth submanifold. This is a submersion, smooth map. So now with all that in place, so it sounds a lot more complicated now than just small category with inverses, but and this is what it means for such a thing to be smooth. Okay, so this is what a Lie groupoid is. Right, so like I said, let me just give a baby example. a smooth vector bundle. Right, so how's that a groupoid? Well, the vector spaces are abelian groups. So it's a disjoint union of abelian groups. So algebraically, that's what it is. Okay, so it's a disjoint union of Lie groups, but they're embedded in a total space. Okay, and so if you have a vector bundle over a manifold, then this is the set of arrows. Oh, shouldn't draw arrows here. Equal. This is the object space, and the range and the source map are the same thing as the base point map. Okay, so two arrows are composable if they're in the same fiber, and composition is just addition. Okay, so it's not a particularly interesting example, but it illustrates what I said before. Like algebraically, this is just a disjoint union of copies of Rk or Ck, depending on your choice of field. Okay, but what makes it an interesting object geometrically is the fact that it lives in the total space, and the operation addition of vectors is smooth from one vector space to the next, very smoothly with the base point. All right. Okay, this is time for the wiping break. See if I can do this quickly. Is there anything to this other than? All of this being recorded. Yeah. All right. It should do. All right. So yeah, so just comment again, since we're not going to go into this. At this level too, there's a appropriate notion of equivalence, which of course is now a little more complicated. It's not just equivalent categories, because you have to somehow take the smooth structure into account. And moreover, that notion of equivalence can be expanded into a appropriate notion of morphisms between Lie groupoids that is not just, you know, the obvious smooth functors or whatever. This was worked out, as far as I know, by Hilsum-Skandalis, that the first people, the first ones I'm aware of. So it's they're sort of generalized morphisms for which this equivalence is an isomorphism. And in some sense, that's really the correct thing in non-commutative geometry, right? Because usually these groupoids represent some non-commutative object which is only well defined up to Morito equivalence, and the groupoid is often only defined up to equivalence in some appropriate sense. Okay. Since none of that plays a role in anything I'm going to do, I'm just mentioning it as a. Okay. Ralph is not going to go into it. I'm not going to go into it. So, but it's there. Okay. I'm going to skip this example because I don't think it matters. Okay. Next. We want to make algebras like I want to do K-theory in the end. So while you can think of these objects, these Lie groupoids, especially if you add these more fancy morphisms, these Hilsum-Skandalis morphisms, as whatever stacks, which is a fashionable, but also very interesting subject. They represent some notion of non-commutative space. In some sense, these are, I think, more geometric than the C-star algebras that we always work with. However, if you want to do K-theory or any kind of cohomology theory for these stacks, you will have to assign an algebra to it. So there's no way around that. So we need to assign a convolution algebra to such a groupoid. Okay? So let me explain convolution. Most people know convolution, but we need to do convolution on groupoids. And it's actually a somewhat interesting. So let me start with, again, with the baby convolution on the finite group, so everybody knows. So the group algebra is sums of essentially group elements, linear combination of group elements. Let's say complex coefficients. Okay, and the key the key defining feature of this algebra is that these are really treated as group elements. So just multiply as group elements, right? These are delta functions, if you like. And this then just linearizes to give you convolution product, right? So the usual. This is the. Okay, so that's convolution in one way. Completely straightforward, but so I want to point out that this here is basically explains everything, and the rest is just an exercise. On a Lie group, however, there's another way to introduce convolution, which is also very, very natural. We have a multiplication map. Right, which is smooth. Since it's smooth, pullback of functions, a smooth function on G is pulled back to a smooth function on G cross G. Right, it's just a dual map. And then, now we dualize again. The dual of C infinity are compactly supported distributions. So, and of course, since it's dual to each of these, whatever they are, spaces, topological vector spaces of the appropriate kind, we get a map, again, in the opposite direction. And this, of course, is by a highly non-trivial theorem, but tensor product of, so this here, despite the notation is not familiar, these are compactly supported distributions. And this map is convolution. Okay, so it's for free. It just says here. I mean, this is also for free, right? So in this, but it arises in a very different way. So if you want to see that this is convolution, okay, let me write down. Let's call this map something. So let's say phi bar G1, G2 is phi of G1 times G2. Just to give this map a name, so it's from phi to phi bar. Then convolution of two distributions evaluated on phi is U tensor V evaluated on phi bar. That's just a way to write the definition. And then just to check that this really is convolution, we need to see what this is and make sure it is the correct thing. So these are now actual delta functions as distributions, but on a Lie groupoid. So this is supposed to be, okay, let me write it somewhat. I don't know how to do this now. Okay. Okay, so you have to evaluate this sort of tensor product of direct deltas on this product, and you get what you want, which is this thing, which is, of course, another delta function value. So it's exactly, again, this thing, but now on a smooth group. Okay? So it's complete. Well, the point here is that this is completely natural. They're not making any choices. There's nothing. Okay, I have to erase again. So what I've been thinking about for a while is to do this on a groupoid, and you can do something like this on a groupoid. No, where's the measure? There's no measure. Yeah, so let me connect it with the familiar. This is not the familiar way of doing it, so I want to not confuse everyone too much. But if you don't know anything, it's an advantage. But if you do, then this is confusing. So how does this connect with, so if you do know groupoids, then this is not the usual way of doing it. So if you have a less elegant way to do this, is you pick a Haar measure, okay, and on a Lie group, that's not a big deal. It's unique essentially up to scaling, okay, so it's not it's almost like canonical. And then a compactly supported smooth function on G can be identified with a distribution because the measure is a distribution. So there's a map which sends a function to the function times lambda. And then if you use this convolution here, you just play a little bit with the formulas, you get the usual formula for convolution of functions. So, right, so I shouldn't use G. Okay, let's use gamma. Gamma is now a group element. G is a function. Okay. Right, the usual thing. Okay, so but I'm emphasizing that here, you should really write d lambda gamma on this side as well, and then add it here, and then you get convolution of two distributions. Okay, so the lambda is just absorbed in the distribution. Yes.
Because on these functions, then if the group is going modular or not, then it matters.
Yeah. Of the star, yeah. Yeah. And it doesn't, oh, I haven't thought it through. So it doesn't for distributions? I don't know. It doesn't? Okay. So I haven't thought about this because on groupoids there's no star in this picture. So. Mine is right invariant. Yes, I wrote it in my notes. Yeah, you're right. All right. It was on my, yeah, it was on my page. Sorry, I forget. Thanks. Yeah, otherwise the formula becomes just slightly different. All right. This is actually, I remember, because I always get confused whether it's left or right, and if this is the correct formula for left or right. But this formula there's only one correct formula, and then if you try to change this into this, you need to use the right invariance. I think on this side, this is a beta inverse on the right. Okay, so convolution on group, but now we want to do it on groupoid. And here things are, okay, so here the Haar measure is not a whole big deal, but on a groupoid it's somewhat more involved. So let me save the details of the convolution of distributions for another day. So it can be done, and it's essentially the same formula, but the formula is very confusing. You have to make sense of the formula, but there's a way to make sense of the formula, and then it's the same. However, let me stick to the familiar first. So the familiar way to do convolution on groupoids is to generalize this picture here and generalize the idea of a Haar measure to a Haar system. So we're going to use formula. I have to give it a name. The star is gone. No, there's a star there. So it's two stars. This formula is convolution. So now you have to just try to make sense of the formula and see how, what this whole thing could possibly be. Since we multiplying gamma with beta inverse here, they have to be composable. If this is beta inverse, then here's beta. So we see that beta and gamma have the same source. And so this lambda, see if gamma is fixed, the beta ranges over the source fiber of gamma. And so lambda has to be a measure on the source fiber of gamma. So again, I can never remember if you're supposed to put the x up or down, so I'm going to put it down. Ralph, is that correct?
Down is correct for source fiber.
Thank you. Okay, good. Okay, so that's what the lambda is supposed to be, but of course you need one for every x, for every object. So you get a Haar system. Not just one measure, but a whole bunch of them. So for each object, x in the unit space or object space, we have, so since we want everything to be smooth, we're going to pick not just measure, but a density. So that's just a smooth measure. Okay, so not a half density. So there's another world of half densities, which I think only exists in France, but I want densities. Okay, so just again, if you know something, this might be confusing. If you don't, then forget what I said. So this is a density on the source fiber at x. So you have a whole family of them. I have to keep erasing. I need to start writing more. Maybe I should scribble more, but I don't know if that records. Oh yeah. Okay, so you want these lambdas to vary smoothly with x. Okay, what does that mean? Well, an easy way to do this is you take a smooth function, a compactly supported smooth function on G. Then, okay, so G is fibered by S. So in every fiber, you can evaluate the appropriate lambda x. You get a number. This depends on x, so you get a function on the unit space. That should be a smooth function. Okay, so lambda as a totality maps C infinity G or to C infinity of G naught. That's the requirement, and that's the definition of it being smooth, a smooth family, if you like. So this is just introductory, so whatever, it's already too technical in some sense, but so it has to be smooth. And then, thanks to Ralph, we know that this has to be right invariant. So this also needs to be right invariant. So you have to think about what it means to be right invariant on the groupoid. So right, it has to be right invariant because I'm using this formula. So this means, okay, let's say you have the base, then you have your source fibers. If you multiply, okay, so what's a nice picture here? So here's a gamma. Multiplication on the right sends any element in this source fiber to an element in this source fiber. Okay, so multiplication on the right with gamma is a map from this fiber to this fiber, and according to all the axioms that we wrote down, it's actually a diffeomorphism. So right multiplication is a diffeomorphism from one source fiber to another, the range of the arrow to the source of the arrow. Okay. And so then right invariance just means that the density at this fiber is identified with the density on that fiber via that diffeomorphism. That's right invariance. Okay. So it's okay. Some arrows will have the same, will be automorphisms, so they will have the same range and source, and that then is a little bit more like Lie group, like a Haar system invariance. Okay. But in this case, you also have identification of different fibers, by right multiplication. Potentially. All right, so that's those three are. This defines a Haar system. Now, if we were doing locally compact Hausdorff groupoids, then existence of a Haar system is not guaranteed. That's an annoying fact, but in this case, everything's nice. It's smooth. You can always pick a smooth Haar system. Okay. So they always exist, but there's, of course, they're not unique in any sense whatsoever. Right? There's no. It's just you have to pick one. All right. So with that out of the way, then this formula is the same. This is how you interpret this formula. So the technicality is to make sense out of what a Haar measure is in this context. And then as a remark, if we're on a groupoid, you take a compactly supported smooth function, and were to do the same thing as here. You take your function and you multiply it with the Haar system. What sort of thing do you get? Well, it's not a distribution on the groupoid, but it's a family of distributions. Okay, one in each source fiber. So let's call this thing something. So these are smooth families of compactly supported distributions in the source fibers. Okay, now with annoying, this took me a long time, but this formula actually works. So you can convolve these guys. This is a convolution algebra. And the reason I never think much about the star is this is very obviously not a star algebra, because if I star this thing, which means replacing gamma with gamma inverse, so f star of gamma is f of gamma inverse complex conjugate. Right? So if you do an inverse, then source fibers change into range fibers, and so you get the wrong kind of object. So the star of this kind of thing is not well defined. But for many purposes, especially if you study later on, we'll study pseudo-differential operators, their kernels are of this type. So the fact that it's a convolution algebra is sufficient for many of my purposes. So this, what I want to say is, just as an aside, you can do something like convolution of distributions on groupoids, but these types of distributions. And then again, you don't need a Haar system. Or the Haar system, if you like, is interpreted as a family of distributions. All right. All right, any questions? Yeah. Yeah, you want an example? Okay. That's a good. To do this whole thing again. Maybe I'll do one at a time. Is that not a good idea? No, it's maybe not a good idea. Okay, example. Let me just use the only two groupoids that I'm going to make use of. The pair groupoid M cross M, where M is a smooth manifold. Okay, that's a smooth groupoid. The object space is M. Arrows are pairs of points. Okay. This is obviously itself a smooth manifold. All the maps are smooth. Let me not bore you with the details there. It's totally trivial. So what's a Haar system here? Okay, so first of all, what is this? This is the S inverse of x being a point in M in this case. So this is, since the source, remember the source is on the right, so this is just a copy of M. So we need a family of densities on M. Now they need to be right invariant. So what's right invariance? If you multiply this on the right with something, you get just like the something being the pair xy. And this is just mapped to M, and not any other source fiber. Okay? So right invariance in this case just means you have to pick the same density on every copy of M. So you pick one density on M and you just repeat it on every guy here. That's a Haar system. Okay, and yeah, then it's an exercise to check what convolution becomes, and it just becomes composition of Schwarz kernels. Yeah. Sorry? Yes, in this case you can, yeah. If they're smooth functions, maybe, yeah. But I don't think that generalizes. Hmm? Sorry? No, it has. Well, I'm picking smooth ones, right, for my own perverse purposes. But yes, as soon as you go, so in the smooth world, it's unique up to at least some flabbiness. But if you go to locally compact, it's a mess. So as far as I know, I don't think there's any. You can pick, you can pick all kinds of measures there, like, discrete ones. And
Locally compact case, you can pick any measure. You could pick a set of points and take some
yeah.
some weights and conversion.
Yeah.
Or you could take some kind of the equivalent manifold. They're all fine in local compact case. In the Leo case, since you take density, you should assume density to be nowhere zero because otherwise
Yes.
they're not quite unique.
Yes.
But anyway, you want to assume it properly, and then
I am saying that. Yeah.
if you assume density, then they are given by the quotient is a smooth function positive. So they are given by particle zero. And so you get isomorphic convolution.
I mean it to be positive, yeah. So yeah, exactly. Sorry. Yeah, the interesting thing is, by the way, if you do the convolution picture, there is such a thing as a smooth convolution, right? A smooth distribution. Okay, and that's a canonically defined thing. And then suddenly you have, like, there's a canonical definition of convolution of smooth distributions. Of course, it's completely isomorphic to the smooth function, but not canonically isomorphic to the smooth function. You have to pick a particular measure, and that's kind of the same here. Okay. So yeah, the French schools to go to half densities to get a canonical convolution product, but you could also go to smooth distribution. They have a canonical convolution. All right. Anyway, that's all just, who cares? But there's actually advantages to this distribution picture. When see, Schwarz kernels are typically not smooth functions; they're distributions. So this is actually useful. Okay. All right. Where am I? Not here. Where are my notes? Oh. Okay, so yeah. In this case, it's unique up to nothing.
No, I mean like in the general groupoid case.
Yeah, it's unique up to nothing.
Although the Haar system is so non-unique.
Yeah, but it doesn't affect anything. Like I said, it's isomorphic to the convolution algebra smooth distributions in the sense that I defined before. And that's completely canonical. So they're all isomorphic. They're not, again, in the locally compact Hausdorff case where you have, you pick measures, that's a much messier object. They're not isomorphic, and as Ralph explained, then they will be Merida equivalent by a deep theorem. But the fact that they're all isomorphic is not a deep theorem. That's quite trivial. If you stick to densities, everything's being smooth. Yeah, so the convolution algebra, the smooth convolution algebras. This thing is well defined. So either you think of it as functions, and you have to pick a Haar system, and different Haar systems give isomorphic algebras, not just Merida equivalent. Or you think of it as smooth families of smooth distributions, and then it's canonical, whichever way you like. Okay. But it's a well-defined thing. Okay, so now, depending on what you want to do, and for the talks, I'm going to use K-theory of C-star algebras, so I want to make this into a C-star algebra. So first it has to be made into a star algebra. And there are two ways, and one I can never remember, and the other one is easy, so I'm going to use that one. So there's a star, and it's basically the inverse f of gamma inverse, and then you take the complex conjugate. There's some other way that you have to stick in some analog of the modular function there. Okay, so then we have a star algebra, and then it needs to be completed. And one way to complete it, it's just good enough for me, is by using the regular representations of the groupoid. That won't be any good as a window cleaner, I can tell. Okay, so this algebra can be represented by Hilbert space bounded Hilbert space operators. But since we're on a groupoid, it's not going to be represented on L2 of G, but on L2 of the source fibers. And so there's a bunch of representations instead of just one. Okay, for a group, there's just one regular representation. So here we have, for every object or unit, our Hilbert space is the L2 space of the source fiber with Haar, whatever, Haar measure, Haar for that particular fiber. And then for a smooth function, and an element in this Hilbert space. Let's pick a smooth one so the formulas all make sense. Okay, so then the representation is essentially convolution, but just let me write the formula just so you see that. Right, so it's essentially f convolved with u, except u is only defined on one fiber instead of on the whole thing. And since convolution is associative, this is a representation, so it's sort of straightforward. So then we define the reduced C-star algebra by completing in this norm, right? So the reduced norm of the function f is the supremum of all these norms. And now we have a C-star algebra, just by completing. All right, so let me complete the example that we started up there. Pretty much already indicated what's going to happen. It is worth mentioning, I don't know how much time Ralph's going to spend on groupoids, that if two Lie groupoids are equivalent in the appropriate sense, okay, so equivalence of categories has to be adapted to smooth groupoids, but it can be, and then the C-star algebras that you associated to it will be Marie equivalent. And this is, as far as I know, this is how you prove, for example, that in the locally compact Hausdorff case, that the C-star algebra is well defined up to Marie equivalence independent of choice of Haar measure, because you have two groupoids, they're equivalent because it's the same groupoid. And okay, the theorem about equivalence of the C-star algebras doesn't say anything about the Haar measures. So you can pick one Haar measure on the left and another Haar measure on the right, and then that theorem says they're Marie equivalent C-star algebras. So, but it's a fairly deep theorem, as far as I remember. Okay, in that case. All right, so as an example, easy example of this, and then I'll stop, maybe even before my time's up, which would be pleasant. So this guy, M cross M. Well, okay, so let's just believe that it's equivalent to a point, okay? So because it's an equivalence relation where every point in M is identified with every other point in M. There's no automorphism group, because okay, it's a pair groupoid. And so this is equivalent to the one element group. Okay, so this should mean that its C-star algebra is Marie equivalent to the C-star algebra of the one element group, which is C. That's a priori. Well, sorry, after having proven the theorem. Okay, and it's still non-trivial to compute this. Well, depending on your definition of trivial, it's non-trivial to compute this C-star algebra. So let's do it. So I have the, I explained to you what a Haar system is. It's basically one density on M, repeated in all the fibers. Okay, so my Hilbert space, this is supposed to be this, but since this is independent of X, it's really all the same Hilbert space. And as it turns out, this formula for convolution, what am I doing? Okay, so how is this to be interpreted? So this here is really y comma z, where we suppress the z, okay, because it's supposed to be a groupoid element. So this, see, this is really this thing, but of course which we identify with L2 of M. Okay, and then this is the integral over M of f yz uz d lambda z, where this is really u of zx, right? And this is yz times zx. There's some beta inverse somewhere which I didn't write down, so I'll leave it up to you. Right, this is really d lambda x of z comma x. Okay, but anyway, it reduces to the familiar formula of the action of a Schwartz kernel on a function on the Hilbert space. So the point being here that pi x f is the operator on L2 of M with Schwartz kernel f. Right, f is a function of m comma m times m, so it's just orthogonal. And okay, then okay, these are compactly supported smooth functions, so they're in L2. If the kernel's in L2, you get a Hilbert-Schmidt operator. A Hilbert-Schmidt operator is compact. And there's certainly enough of them in there that if you close it up, you get all the compact operators. Okay, so the C-star algebra is somewhat canonically isomorphic to compact operators on L2 of M. So basically here, for every x, you get essentially the same representation, or equivalent representation. All right, so that also then proves this Morita equivalent by direct computation. Okay, but all right, so I think I'll just stop. So questions?